This video is on calculating concentrations of solutions, and it's the first video that we'll watch. Today we're only going to talk about molarity. First thing, what is concentration? Well, that's the ratio of the amount of solute to the amount of solvent. So if something's concentrated, it has a lot of solute in a certain amount of solvent. You can dilute that by adding more solvent, and so something that's dilute has a little bit of solute and a lot of solvent. And what is dilution? Dilution is increasing the amount of solvent to decrease the concentration. So if I'm making orange juice from concentrated orange juice, to water it down, I would add water. So that would be diluting it, making my orange juice that I can drink. Okay, our first set is in terms of molarity. Now you need to write down the molarity equation. And it's really not so much an equation, but it tells you about the units. For molarity, you have moles of solute per liters of solution. Now, it's just one way to express concentration. There are many ways to express concentration. Important part here is what it says in terms of solute or solvent or solution. So be careful that you realize it's moles of the solute on top and liters of solution on the bottom. Here's our first example. Calculate the molarity of a 150 milliliter solution that contains 50 grams of sodium chloride. I believe it's important to figure out what you're dealing with in terms of solute, solvent, and solution, and how does that factor into the equation or into the set of concentration units that you need. So first, for solute, looks like we have 150 milliliters of solution. We have sodium chloride. Now, sodium chlorides are solid, and as often when you have the solid, that ends up being your solute because you're adding that to something like water to make a solution. So 50 grams of sodium chloride is my solute. Solvent, we can assume that this is water, but if we look at our molarity equation, it's solute and solution, so we really don't even need the solvent, so we'll just put Na, not really necessary. For solution, it says we want 150 milliliters of that solution. Okay, once you identify what you're working with, then you want to make sure your units are correct according to your equation. So we have solute in terms of grams, and what we need is moles. So we'll change those grams into moles. For the solution, we need liters, and we have milliliters, so we'll need to change that into liters. So let's do that. 50 grams of sodium chloride. Well, how do I change grams into moles? We need the molar mass. So if I add up 1 sodium and 1 chlorine, 22.99 plus 35.45, those are their atomic masses from the periodic table, I get 58.44 grams, and that's equal to a mole of sodium chloride. Cancel my units, and I end up with 0.856 moles of sodium chloride. Now I need to move on to the solution. We want to change that into liters. We have 150 milliliters. I know that in 1 liter there are 1,000 milliliters, so we'll put the 1,000 milliliters on the bottom so that it'll cancel. And cancel my units, and you end up with 0.15 liters. Great, now I have moles and I have liters. All I need to do now is figure out the molarity. So here's what we'll do. We'll take the moles of the solute, divide by the liters of solution. So molarity is equal to 0.856 moles divided by 0.15, and I get 5.7 moles for every 1 liter. So that means in this solution, if I have a liter of this solution, there will be 5.7 moles in it, moles of sodium chloride. We can shorten that and just say it's 5.7 with a capital M. That capital M is for molarity, and it actually is going to make a difference whether you have capital M or lowercase m's or mole. So that's our answer. And the way you would say this is we have a 5.7 molar solution. Okay, second example. Again, we're still dealing with molarity, And this time we're figuring out the volume. So we're not figuring out the molarity, we're figuring out the volume. It says we want the volume of a 4.2 molar hydrochloric acid solution necessary to get 1.5 moles of HCl. Again, I'm breaking it down into solute, solvent, and solution. So the solute says we want 1.5 moles of HCl. The solvent, since we're in terms of moles and liters, not really necessary. Or excuse me, solute and solution, not necessary. For the solution, we have 4.2 molar HCl solution. I'm going to show you two ways to work this problem. I find it easier to use stoichiometry or dimensional analysis to work the problem. You might work the problem using the equation. I will show you both ways, and then I will continue to use a conversion in order to solve these problems. Okay. All right, so when we have 4.2 molar HCl solution, what that's really saying is that for every 1 liter, we have 4.2 moles. So you have to imagine 4.2 moles in a liter of solution. We can use that as a conversion factor. We can write it as is with the 4.2 moles on top, or put the 4.2 moles on the bottom and the liter on top. Let's see what we need to do in our situation. So you'll start with the other thing that's not a conversion factor. You'll start with the moles of solute. Or if I had liters, I would start with the liters of solution. Okay, so we're going to start with 1.5 moles of HCl. And we're going to use this, the molarity, right here, to convert that into liters of solution. So I'm going to multiply that by this as a conversion factor. Okay, so I just need to decide, am I going to write it as is or if I'm going to flip it? Well, if I want moles to be on the bottom, I'm going to have to flip this. So I'll put the 4.2 moles on bottom and the 1 liter on top. Cancel my units, and I get 0.36 liters. Done. The problem's done. If using a conversion factor gets a little confusing for you, you can always go back to using the equation. Molarity is moles of solute per liter of solution. So what I'd do is I would take the molarity is equal to the moles of solute, 1.5 moles, over X, the liters of solution that I'm trying to figure out. I would cross multiply. Okay, and I need to keep all those units with me. That's why I think it's a little harder because it's units, carrying those units. I'd move the 4.2 moles per liter to the other side. So I'd divide both sides by that. Those cancel, and you're left with X is equal to 1.5 moles over 4.2 moles per liter. Same thing that happened in the previous example or setup. That works out to be 0.36 liters. Again, mole cancels, liter is going to end up on top. Okay. Example number 3 is asking you to prepare a solution, and this will be important when we prepare solutions in lab. So how do you prepare 5 liters of a 2.0 molar aqueous solution of KCl? Okay, again, breaking it down. Solute. So we're looking at potassium chloride, KCl. That's going to be the solid. It's definitely the solute, the solvent. Now, in the past, we just said we don't need that for the equation, but we need to prepare the solution, so we definitely need to know what the solvent is. This is aqueous, which means it's dissolved in water. Now, all the information is actually for the solution. We've got 5 liters of a 2.0 molar solution. So all of that's going to go here. Okay. So what do we need to do with the information? Well, KCl. We're going to end up with moles of solute, which isn't something you can measure directly, but you can measure grams. So we'll need to get that in terms of grams. For the solvent, okay, we'll need to figure out how much water. Maybe liters, milliliters, either one of those. For the solution, again, we're going to turn that into a conversion factor that since it's 2 molar, that means that there are 2 moles in every 1 liter. Okay, so we'll start with the 5 liters that we have. It's the only other number value that I have that isn't made into a conversion factor. So we've got 5 liters times the molarity. Now I want to see if I'm going to use it exactly as I have it written, as 2.0 moles over 1 liter, or if I need to flip it. Well, liter needs to be on the bottom so that it cancels, so we'll just leave it exactly the same. Liters cancel, and we end up with 10 moles. Okay, what do we do with that? Well, that's 10 moles of our solute. Remember, it's moles of solute over liters of solution. So we're going to convert the 10 moles of solute, which is KCl, into grams so that we can measure those grams. So I need the molar mass of potassium chloride. I know that 1 mole of potassium chloride, look it up on the periodic table, ends up being 74.55 grams. And that works out to be 750 grams of potassium chloride. So what do we do with that? Well, we need to know how to make the solution. So here's the rest of this. How do you prepare the solution? Well, this is kind of an outline of how you prepare any solution. You're going to add a certain number of grams to a container, and you want to make sure that that container holds as much of the solution that you need. So here's some steps. Okay, you weigh it out, you stir it. If you have a volumetric flask, that's the amount. Volumetric just means it measures that exact amount. This one measures 250 cubic centimeters. You might find one that's a liter. Maybe you could find one that's 5 liters. So we're going to start filling this in according to the information from before. We're going to add 750 grams of potassium chloride, that was our solute, to a container that holds 5 liters. We'll want to fill it halfway with a solvent, which is water, and mix that really good. So if we had a volumetric flask, we would shake it up, and then we would dilute it to the mark. So it says fill the flask to our final volume of our solution is 5 liters. So we'll fill it to the 5 milliliter mark, and we'll mix it again. Maybe not shake it, but maybe kind of stir it just a little to get it completely dissolved in the solution. All right, molarity by dilution is the last one we'll do in this video. There's an equation for that. M1V1 equals M2V2. M, capital M, just stands for molarity, volume, V, and that can be in liters or milliliters. Just needs to be in the same unit for each one of the volumes. Dilutions can be made by taking a high concentration and adding more solvent to dilute it. So here I've got an example. I've got a 10 molar solution and I've got a liter of it. Now I want a 5 molar solution, so I'm going to add water to this. So if I get it up to 2 liters, now I've cut this concentration in half. Now I have a 5 molar solution. Well, what's going on with the moles in here? Well, if this is 10 molar and this is 1 liter, then there's 10 moles of solute in here. If I dilute it by adding water, I still have 10 moles of solute, but with the 2 liters there, now I've reduced the concentration to 5 molar. So the number of moles aren't changing when I'm diluting it. It's just the concentration that's changing. So here's our example. What volume of a 15.8 molar nitric acid solution is required to make 250 milliliters of a 6 molar solution? I'll list my givens. Oh, M1. So what does that mean, the ones? The 1 just means the initial, or what it's starting at, the first set. And then 2 just means the second set, just like when we're doing gas laws. The first set of conditions and the second set of conditions. So volume 1, it says what volume, so we don't know what volume. It says of, so that attaches those two. M2, it says we want a 6 molar solution in the end, and we want 250 milliliters of it. Here's our equation, M1V1 equals M2V2. I want to solve for V1, so I'm going to divide both sides by M1, and it just makes this look like this. I plug everything in. The molarities will cancel. And if I solve that, I get 95 milliliters. So what that means is if I want to take and make a new solution, I would take 95 milliliters of the 15.8 molar and put it in a volumetric flask that is 250 milliliters and fill it to the 250 milliliter mark with some water. And that's it for molarity.